Welcome. This is a comprehensive guide to measuring and understanding artificial intelligence performance across different domains. We will be looking at evaluation metrics for classification, regression, generation, and robustness of the models. First, let's discuss accuracy. Accuracy is the proportion of correct predictions among the total number of cases examined. The formula for accuracy is accuracy equals true positives plus true negatives, divided by true positives plus true negatives plus false positives plus false negatives. Here's an example using scikit-learn library. From scikit-learn metrics, import accuracy score. Then, calculate accuracy using the accuracy score function with y_true and y_predicted as arguments. Finally, print the model accuracy, formatted to 2 decimal places. Now let's delve into precision. Precision is the proportion of positive identifications that were actually correct. The formula for precision is precision equals true positives divided by true positives plus false positives. Here's an example of calculating precision score using scikit-learn. From scikit-learn metrics, import precision score. Then, calculate precision using the precision score function with y_true and y_predicted as arguments. Print the model precision formatted to 2 decimal places. Let's talk about recall. Recall is the proportion of actual positive cases correctly identified. The formula for calculating recall is recall equals true positives divided by true positives plus false negatives. Here's the Python code. From scikit-learn metrics, import recall score. Then, calculate recall using the recall score function with y_true and y_predicted as arguments. Finally, print the model recall formatted to 2 decimal places. Now let's dive into F1 score. F1 score is the harmonic mean of precision and recall, providing a balanced metric. The formula is F1 equals 2 times precision times recall, divided by precision plus recall. Here is an example using scikit-learn. From scikit-learn metrics, import F1 score. Then, calculate F1 using the F1 score function with y_true and y_predicted as arguments. Finally, print the model F1 score, formatted to 2 decimal places. Now let's explore regression metrics starting with mean squared error, also known as MSE. Mean squared error is the average squared difference between predicted and actual values. The formula is MSE equals 1 divided by n times the summation of y_true minus y_predicted squared. Now consider this Python code example. From scikit-learn metrics, import mean squared error. Then, calculate MSE using the mean squared error function with y_true and y_predicted as arguments. Finally, print the MSE formatted to 2 decimal places. Next, we have mean absolute error, also known as MAE. Mean absolute error is the average absolute difference between predicted and actual values. The formula for MAE is MAE equals 1 divided by n times the summation of the absolute value of y_true minus y_predicted. Here's the Python code. From scikit-learn metrics, import mean absolute error. Then, calculate MAE using the mean absolute error function with y_true and y_predicted as arguments. Finally, print the MAE, formatted to 2 decimal places. Let's talk about R-squared, also known as R-squared. R-squared is the coefficient of determination, representing the proportion of variance explained by the model. The formula for R-squared is R-squared equals 1 minus the quantity SS_residential divided by SS_tot. Let's consider the Python code for calculating R-squared. From scikit-learn metrics, import R2 score. Then, calculate R-squared using the R2 score function with y_true and y_predicted as arguments. Finally, print the R-squared score, formatted to 2 decimal places. R-squared ranges from 0 to 1, where 1 indicates perfect prediction. Next, let's discuss root mean square error, also known as RMSE. Root mean square error is the square root of MSE, providing an error metric in the original unit scale. The formula for RMSE is RMSE equals the square root of the quantity 1 divided by n times the summation of y_true minus y_predicted squared. Let's understand this with an example. From scikit-learn metrics, import mean squared error and import numpy as np. Then, calculate RMSE by taking the square root of the mean squared error function with y_true and y_predicted as arguments. Print the RMSE, formatted to 2 decimal places. Lower RMSE values indicate better model performance. Let's discuss generative AI metrics. First, let's dive into BLEU score. BLEU, which stands for Bilingual Evaluation Understudy, measures the quality of machine-generated text by comparing it with reference texts. It compares n-gram overlap between generated and reference texts, and scores range from 0 to 1 where higher scores are better. Here's an example of calculating BLEU score. From NLTK Translate, import sentence BLEU. Set the reference to the quick brown fox. Set the candidate to the fast brown fox. Calculate the score using the sentence BLEU function with reference and candidate as arguments. Then print the BLEU score, formatted to 2 decimal places. Now let's look at the ROUGE score. ROUGE, which stands for Recall-Oriented Understudy for Gisting Evaluation, evaluates generated summaries against reference summaries. It measures recall, precision, and F1 score of overlapping units. There are multiple variants of ROUGE, such as ROUGEN, ROUGEL, and ROUGES. Here's the example using ROUGE score. From ROUGE_score, import ROUGE score. Set the score to ROUGE score with ROUGE1 and ROUGEL as arguments. Calculate the scores using the score function with reference text and generated text as arguments. Finally, print the ROUGE1F measure, formatted to 2 decimal places. Let's explore more generative AI metrics, starting with the METEOR score. METEOR, which stands for Metric for Evaluation of Translation with Explicit Ordering, evaluates translations by considering stemming, synonyms, and paraphrases. It considers word order and semantic similarity and handles stemming and synonym matching. Here is an example of calculating METEOR score. From NLTK Translate, import METEOR score. The reference is the quick brown fox. The candidate is the fast brown fox. Set the score to METEOR score with the reference and candidate as arguments. Finally, print the METEOR score, formatted to 2 decimal places. Let's dive into BERTScore. BERTScore leverages contextual embeddings from BERT to evaluate text similarity at a semantic level. It uses contextual embeddings for semantic matching and is robust to meaning-preserving lexical variation. Here is an example of calculating BERTScore. From BERT_score, import score. Set references to the quick brown fox. Set candidates to the fast brown fox. Calculate F1 by calling the score function with candidates, references, and language set to English. Finally, print the BERTScore F1, formatted to 2 decimal places. Now let's discuss robustness metrics, beginning with adversarial accuracy. Adversarial accuracy measures model performance against adversarial examples designed to fool the system. We can evaluate the model performance against targeted perturbations that maximize misclassification probability. Here is an example using Python. Import fullbox as FB. Set the model to fb.pytorch model with net and bounds set from 0 to 1. Set the attack to fb.attacks.fgsm. Set epsilon to 0.01.1.3. Calculate the adversarial examples and the success rate by calling attack function. Calculate the robust accuracy by subtracting the mean of the float success by 1. Next, let's examine noise sensitivity. Noise sensitivity evaluates model stability under different types of input noise and perturbations. We have types of noise testing such as Gaussian noise, random rotations, and environmental variations to assess model robustness. Here is an example: import numpy as np. A function named test noise sensitivity takes the model x and noise levels. For each noise level, add normal noise with zero mean and the noise level to the input x. Generate the predictions for the noisy inputs. Calculate the accuracy by comparing the predictions with the ground truth and taking the mean. Add this accuracy value to the results list and return the results. Higher stability across noise levels indicates better model robustness. Let's explore more on model robustness, specifically out-of-distribution detection. Out-of-distribution detection involves evaluating a model's ability to identify and handle data points outside the training distribution. Some of the detection methods are maximum softmax probability, also called MSP, and entropy of predictions. Here's an example of detecting out-of-distribution data. Define a function to detect out-of-distribution data, taking a model data and a threshold as input. Calculate the probabilities using the model's predict-proba function. Find the maximum probability for each data point. Determine if the maximum probability is less than the threshold. Then return the result. Now let's discuss model calibration. Model calibration assesses how well model confidence aligns with its accuracy. We have various calibration metrics: expected calibration error, also called ECE, and reliability diagrams. Here's an example of how to use it. From netcal.metrics, import ECE. Calculate the calibration score using the ECE function measure with the predictions and ground truth as arguments. Well-calibrated models should have confidence scores that match their accuracy rates. Let's explore some evaluation best practices. The first best practice is to use multiple metrics. Combine different evaluation metrics to get a comprehensive view of model performance. Another best practice is to apply cross-validation. Implement k-fold cross-validation to ensure robust evaluation across different data splits. A best practice is to make sure that you do regular re-evaluation. Continuously monitor and re-evaluate model performance as data distributions change. Now, some key considerations are: ensure test data represents real-world scenarios and edge cases. Consider task-specific metrics that align with business objectives. Balance between different performance aspects such as accuracy versus robustness. Document evaluation methodology and metrics for reproducibility. Account for ethical considerations and potential biases in evaluation. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.